Hello. Gunesh, are you?
Hello, good morning.
Hello, ciao.
Hi, Christoph. How are you?
Hello, Gunesh. Is my pronunciation correct?
It is correct. Thank you.
Gunesh. Okay, good.
Yeah.
Because of course that's something I cannot exercise by email.
That is true. Yeah, with all the Turkish accents here and there.
Okay, good.
Yeah. Hello, Mansour.
Hello, Mansour. You're not you're mute, Mansour.
Bonjour à toutes, bonjour à Montréal, bonjour à la Belgique,
Bonjour.
Bonjour à la Turquie, bienvenue à la 12e session de Terahertz Days. Je m'appelle Mansour. Hello everyone. Good morning to Montreal. I guess good afternoon to Belgique.
Yep.
Belgium. And good evening to Turkey. Welcome to the second session of Terahertz Days. So before starting and introducing our workshop chair and our respective speaker, I just want to sync up a few things with our co-hosts. So just to confirm that, Professor Christophe, do you have access to share your screen?
Yes, sure.
Okay, perfect.
You want me to make a test? Let me test that, huh?
Yeah, test.
Share screen, though I'm pretty used to Zoom. There should be no problem. Well, I think I'm sharing the whole screen at this point. Yes, huh? Can you see my screen?
Yes, yes.
There is yeah, and you can see the slides,
Yeah,
right?
yes, thank you.
Okay, good.
And Professor Ganesh, can you sync up with you as well?
Of course, so let me. Oh, okay. Christoph, can you stop sharing?
Can you please stop sharing right now?
Yeah.
Okay, I think it is working.
Okay, perfect. So, okay, I guess it's my turn to share a screen and just warm up the event and start, and then hand over microphone to our workshop chair. So just give me a second.
Mansour, are we just a little bit ahead of time?
Yes, we are, and that's
yes, because I would like to use a couple of minutes to visit the restrooms.
Visit the restaurants?
No, the restroom.
Of course, Christoph. Yeah, we have time.
See you in a second.
Yeah, please.
See you in a second.
Yeah. I thought he's saying the restaurants. Okay. I wish we had Professor Christophe and all the members in person, so we had the chance to at least go to a restaurant. Anyways,
I'm looking forward to those days, Mansour.
Dr. Grinch, can you see my screen?
Yes. Perfect.
Okay, perfect. So once again, welcome to a second session of Terahertz Days.
Mansour, maybe we can start like on time. Just wait for a few more minutes.
Yeah, why not? Yeah, for sure. Let me check to see if how many people are admitted already. So far we have 23. And oh, we have a Professor Shahi. Hello, Professor. Welcome to event.
Hello, how are you?
Hi,
Ganesh. How are you?
Shahi. Good. How are you doing?
Yeah, fine.
Excellent.
Good luck.
Thank you.
So people are jumping to the event right now, and the number is increasing. I see Professor Sharawi as well join. Hello, Professor. Welcome to event.
Yes, hi, good morning, everyone.
Good morning.
How are you guys? Mohammed.
Hi, Ganesh, good morning. How are you guys doing?
Very well. Ready to go.
Excellent. It's Christoph there. Good morning, Christoph.
He'll be back. Oh, he's back already. Oh,
Happy New Year. How are you doing?
Yes. Okay, Happy New Year. Fine. You had a good start. So is there a lot of snow in Montreal?
Yes, this morning. Yeah, there is, I don't know, so far, I think 20 centimeters or maybe 15 to 20.
Wow.
Yeah. Yeah. So
we haven't
it's
got
gonna
any.
be. It will be a busy afternoon. We're gonna clean up all of that, you know.
Ah, yes. If my talk is not clear, maybe then some people will start cleaning the snow.
Yeah.
All right, 27. So just a few more minutes, maybe 1-2 minutes.
Oh, it's okay. Yeah, okay.
Just
I'm
one.
ready. I'm ready.
So this event is, of course, Dr. Ganesh will introduce the workshop more precisely, but I just want to introduce our co-hosts and where we started. So we established these series of events in last year fall, and we have different co-hosts from Montreal, Ottawa, and Turkey. Star ICOM is sponsoring this event. IEEE Montreal section is co-hosting, and INRS Institute is as well co-hosting this event officially. So Dr. Ganesh, she is professor at Polytechnique de Montréal, and she is the co-host, actually workshop chair of this series. So I guess I should hand over microphone to Dr. Ganesh. There are a lot about her, so I think that would be nice to let her introduce herself more precisely. Dr. Ganesh, I'm going to stop sharing and the floor is yours.
Okay, thank you, Mansour. I'll start by sharing my screen. Now, of course, before we start, as Mansour, you kindly mentioned, we have a number of sponsors for these workshop series, including Star ICOM, IEEE Montreal, and INRS IEEE student branch. And before I would introduce myself, I would also like to thank Mansour, who is the YP IEEE Young Professional Chairs in Montreal, for being instrumental in the organization of the Terahertz Days. So welcome everyone. Good morning, good afternoon, good evening to you. My name is Güneş, and I am with Polytechnique Montreal. I am the chair of this workshop series. I have received my degrees from Istanbul, my bachelor's degree from Boğaziçi University in Istanbul, and the master's and PhD degrees from University of Ottawa. I have been with Polytechnique since last March, and I am very happy to be a part of the I'll say the impressive research infrastructure and my good colleagues in Polygram Research Center. Our director is Professor K. Wu in Polygram, and all our colleagues are working towards complementary research projects in a number of research fields. And for the following years, we will be focusing on terahertz more and more, and that is basically the main motivation behind this workshop series. And why terahertz bands? It's when you look into any of the 6th generation vision papers, you will hear this buzz about the terahertz. The large bandwidth and the high data rate potential, smaller antenna sizes make it very appealing, and it also includes a number of physical challenges, challenges in the device perspective, and it also provides a number of opportunities in terms of the integrated terrestrial, air, and space networks. So our goal in this workshop series is to investigate the hidden potential of terahertz bands from experts' perspective, and we invite world-leading experts in this field to explain their research findings. Our first session was held last November. Professor Angeliki Alexiou was our guest, and she mentioned about how terahertz would be a part of this expected sixth generation network vision. And today we are happy to host Professor Creia from University Catholic de Leuven, and he will be giving us a talk from the design perspective in the in terahertz bands, sub-terahertz bands, to be more specific. And I would introduce Professor Creia with his long biography. Dr. Creia received his Bachelor of Philosophy degree from University Catholic de Leuven, and he also got his PhD degree from UCL in Applied Sciences. From 94 to 99, he was a teaching assistant, and he carried out very interesting research on the radar signature on the sea surface perturbed by rain in collaboration with NASA and ESA, European Space Agency. From 1999 to 2001, he was a PDF in Eindhoven University. He was also with the University of Massachusetts in USA and also Netherlands Institute for Research in Astronomy. In 2002, he started an antenna research activity in the UCL, where he's currently a professor. He was also with the Astrophysics and Detectors Group of University of Cambridge in 2011. His research has been funded by a wide number of bodies, including Région Wallonne, European Commission, European Space Agency, FNRS, and UCL. His current research interests include mutual coupling, finite antenna arrays, and the number of antenna designs. And my favorite is the metamaterial based ones, which we will focus on today. And he also looks at their applications in communication systems and sensing systems. Dr. Creia received George Vanderlanden Prize from the Belgian Royal Academy of Sciences in 2009. He also served as an associate editor of the leading journals, including IEEE Transactions on Antennas and Propagation, and IEEE Antennas on Wireless Propagation Letters. So, Professor Creia, it's a pleasure of hosting you today. We are looking forward to your talk. The floor is yours.
Okay, thank you, Gunesh, for this very kind invitation and very kind introduction. Thank you also to Mansour and Mohammed. So it will be my pleasure to give you one of the many possible perspectives on the Terahertz technologies. I should mention that actually, since we have a rather numerical look at the problems, we are not specifically focusing on terahertz. We have had projects in optical bands also, and let's say most of our current projects are at somewhat lower frequencies because we don't have the fantastic equipment you have in Montreal, but we are looking forward to the possibility to collaborate. My slides are not shared yet, right?
No,
So
not yet.
I should share the slides. So it's an honor for me to be invited by your very well-known group at Polygram. So as I mentioned, I'll give one of the many possible perspectives on this subject. And our perspective is pretty much based on mutual coupling. And to anticipate on the conclusion.
Sorry for interruption, Professor.
Yeah.
Can you swap the screens because we see?
Yes, I'm fixing that. Duplicate slideshow. Yes. Is it okay now? Do you have the slides in full screen?
No, I think it just. Oh, yeah, that's correct.
Oh, it is. Yeah,
okay, good. Essentially, I'll anticipate a little bit on the conclusion, is that actually what appears to be a problem for phased arrays is going to be our main tool when it comes to metasurfaces, and that's actually surface waves. And well, surface waves are all about coupling between a number of patches you print on a given surface. And so I'll give you a somewhat historical perspective while beginning with phased arrays and the analysis of mutual coupling in phased arrays. What our approach is relatively numerical, so we are developing our own software, which we mostly use for our design, but nevertheless, we also sometimes use a CST that depends on the type of materials we are working with. So it's going to be numerical, but I will do my best efforts not to throw tens or hundreds of equations. So I did my best to put the equations only on a few of the slides. Well, as you certainly realized, now we are talking about pretty complex devices, and so it is pretty difficult to use canonical solutions to see how those devices are going to scatter or radiate electromagnetic waves. So we need numerical tools. And I can classify them according to two axes, either differential or integral equation approaches for Maxwell's equation, and either in time domain or frequency domain. You may have heard about FDTD, finite difference time domain. Okay, so that's a differential approach, and we replace the derivatives by finite differences. Okay, it is very popular, but it may not be the best for radiating structures, because you have to add an absorbing boundary around the structure. Integral equations in time domain is let's say, still has some stability issues. It would be fantastic to have those techniques really stable, because when you deal with integral equations, you will have only unknowns on the surfaces. So you just mesh the surfaces and not the volumes. Now, talking about frequency domain, well, what is very popular is finite elements approaches or method of moments. And that's going to be your favorite, because also compared to finite elements, we don't have to add, let's say, absorbing boundary conditions around the structure. Okay, so this is, for instance, a mesh we have of a Vivaldi antenna, so a tapered slot antenna, okay, with a feeding structure here. Okay, and of course the structure is matched with many little triangles, and the whole thing is in a dielectric box. So that's the kind of thing we can analyze. And here the meshing is only on the surfaces, so we don't have to mesh free space. Of course, we end up with much smaller systems of equations. The only price to pay is that they are full system of equations, so they're not sparse, but there are many workarounds to deal with that dense aspect of the systems of equations. Okay, so I'm not sure everyone is familiar with the method of moments. You may have heard about it in your master's courses. Maybe you could raise your hands if you already heard about or have some familiarity with the method of moments. Anyone has been using or working or developing method of moments?
Yeah, I took a course in method of moments with Derek McNamara at the University of Ottawa. So excellent. I have like some knowledge, but you know.
Okay.
Yeah, some of my research has been focused on the method of moments, so I have some familiarity with it as well.
Okay, good. But it may not be the case for everyone, right? So maybe 25% of the audience is familiar with method of moments. Is it maybe Mansour, you can tell me whether, or Mohammad, whether that's a good estimation?
Yeah, I think that's a good estimation.
Yeah. Okay.
Yeah, maybe a little bit more. Yes.
Maybe a little bit more. Okay, that's good. So that means that I can go a little bit faster. But okay, I will nevertheless try to explain it from the very beginning. And I did my best to keep the equations only on a couple of slides. Okay, so essentially, this is what one of my previous PhD students named the smiling sphere. So it's a sphere, and you see it's kind of smiling. So what you see there is the currents on the sphere when a plane wave is hitting the sphere. So how is that analyzed? Well, essentially, you say that the unknown currents correspond to a superposition of already determined basis functions. So the most popular basis functions are Rao, Wilton, Gleason. Okay, so they are defined over two consecutive triangles. Okay, and they flow, as you can see, with the little arrows there. So there is one here, there's another one here, there's another one here, and so on. Okay, so they overlap each other. Those functions are known. Of course, with that, you don't know yet what is the induced current. The induced current is going to be written as a linear combination of those functions with scalar coefficients which need to be determined. So the whole goal of the method of moment in the end is to find those x coefficients for a given excitation of the object. Okay, so as I said, I did my best to put all the equations on one single slide. So then when we are ready with it, we can, let's say, talk about the pictures. So this one I already mentioned. Okay. Now you can say, well, if those currents are known, okay, which is not fully the case, they are known, but you don't know those coefficients. Okay. Well, then you can compute the radiated fields. By the way, we use a vector potential. I'm sure you heard about that before. So it's a convolution between the scalar Green's function, E minus jkr over r, okay, r being the distance between source and observer. So convolution between scalar Green's function and the current distribution. We don't know j yet because the x's are unknown, but of course you can put the sum in the integral and then swap the sum and an integral, okay, and you're going to have a sum of the x's multiplying those things where each j is one of the known basis functions. Okay, and then, well, from there, if you can compute derivatives, okay, versus space, you can compute the electric and magnetic fields. And so what does the method of moment do? Well, it essentially enforces the boundary conditions on the interfaces. If my smiling sphere is metallic, then I just need to say that at every point on the surface, the total electric field, so it means the incident electric field, for instance, a plane wave, and that scattered electric field, so re-radiated by those currents, that sum is going to be equal to 0. Okay. Now, there is a little trick with the method of moments. We could say that, okay, suppose we have 10,000 basis functions, okay, we do that at 10,000 points, and we are ready. Okay, well, we impose that the total electric field is 0, tangential electric field is 0, okay, over the 10,000 points. Now, it's not the most stable approach. Okay, it is better to impose those fields equal to 0 on the average, and it's a weighted average, and it's weighed by some testing functions. By the way, it is pretty stable, and it has many advantages to use the testing functions that are identical to the basis function. So your list of testing functions is also the list of basis functions. And so then it's simple, you impose this boundary condition on the average after integration over a testing function. Okay, so that allows you to have the condition satisfied properly in an average sense. And of course, it allows you to write as many equations as you have unknowns, because you have as many testing functions as you have basis functions. I will skip the, let's say, implementation details, because I don't want to kill you with this. Well, some of you already know the tricks probably, but you essentially put this equation in this one in this one, this one in that one, okay? And you end up with a square system of equations, okay? The unknowns are still the x there, and you have one equation per testing function you have been considering. And let's say for people developing methods of moments, most of the work consists of calculating those relatively boring integrals where you have the basis function here, the Green's function there, and the testing function. And where it gets a bit tricky is that this Green's function is singular. So when the observation point R is getting close to the source point, well, it behaves close to 1 over R, and you have to integrate analytically or numerically this singular integral. Of course, it's an integratable singularity, okay? And so there are many tricks to be able to integrate this, to calculate those integrals. Of course, I'm not going to bother you with these integration tricks. We are rather going to see how this applies to periodic structures, to eigenmodes, how this allows us to analyze phased arrays, including all the effects of mutual coupling in the phased array, and then how this allows us to analyze metasurfaces, and finally, how this allows us to design metasurfaces. Okay, so any question about the scope of this presentation? So please don't hesitate to interrupt me. If you have a question, please raise your hand, or just speak through the microphone, because I would like to make sure that that people essentially follow me. And contrary to let's say a talk in presence, I cannot see in your eyes if there are big question marks in your eyes. So please don't hesitate to interrupt me. So
Christoph, maybe I can interrupt, but not for a question, but for the audience. You can, if you prefer, you can also type your questions to the chat box, and you can follow up.
This supposes I open my chat.
I can follow with Christoph.
Yes, then warn me, because since I am in full screen, I'm not sure I can see the chat, or I'm going to let's say hide a bit my slides with the chat, but then inform me, please. Yeah,
of course.
Okay, good. So I would like to show you an example where the effects of mutual coupling are actually extremely mild. Okay, so you have just 8 dipoles here, and the distance is half wavelength. So the most basic array of dipoles you may use to do direction finding or communications. So pretty basic stuff. And here are the radiation patterns presented in perspective. Okay, so one dipole is at the center here. No, this is for the infinite array. This is for element 1, element 2, element 4. Okay. And as you can see, the shape of the radiation pattern is far from being azimutally symmetrical. So if I had just one element, it would be just a circle here. Well, you see it's very different, and from one element to the next, the difference can be pretty big. And by the way, if you put the elements closer, or if you have a kind of an eigenmode that is circulating along the periodic structure, those radiation patterns are even much more distorted. So that means that mutual coupling is not just a side effect. So this is a very mild mutual coupling, but yet if you want to use this array to do accurate direction finding, you have to include the definition of all the radiation pattern to have an accurate result. Otherwise, you are not going to go better than 2 to 5 degrees of accuracy. If you want to reach 1 degree, you must include, let's say, the definition of all the radiation patterns. And our colleagues in signal processing, they know how to include the radiation patterns. But the goal is, in the first instance, is to calculate, preferably efficiently and accurately, those different radiation patterns. By the way, you may also put the antenna in an infinite array. So you excite just one, the other ones are passively terminated. So the load could be just the input impedance of the amplifier. And then, well, you get this. And you see, okay, in the direction of the other elements, the radiation pattern is much more narrow than in the direction orthogonal to the array. And so that's what we spend our lives analyzing. And if possible, for pretty challenging arrays that are, let's say, coupling even much stronger than arrays of dipoles. And then, well, kind of naturally, we arrived at metasurfaces, which are also big arrays, so to say, which by nature support surface waves. For some reason, I can't. Okay, good. What about infinite arrays? Well, for infinite arrays, we play a little trick. We analyze the currents on just one element, but whenever we talk about a source, well, we consider the source on that element, but also that equivalent source on all the other elements. Okay? So that means that we have to include A minus jkr over R, but R is the distance between a source and an observer on the dipole of interest, but also the distance between the same source but on another element and the observation point on the dipole of interest. And then, okay, also another term with respect to this antenna. So we kind of duplicate the source on all elements, and we have to add up all these effects. So all the fields radiated by the sources located on the different elements. Now there's a pretty vast literature about how we compute, how we add up those A minus jkr over R. So it's this thing, okay? But we have to consider sources located on the same antenna, but also on all the other antennas, okay? And there are an infinite number of them, okay? Of course, we could just write here a summation symbol, pardon, okay? And the different distances associated to the sources located on consecutive elements. Unfortunately, that summation converges extremely slowly. Okay? So you need millions of terms to have 3 correct digits. So it's truly impractical. And so there are several techniques that are described in the literature. I won't spend too much time on them because it's well, it's a kind of nitty-gritty mathematics. We developed one that has some physical background, so to say. We view the infinite array, so it's an array that is infinite in 2 directions. Okay, we view it as a number of line sources, and actually, it's possible to write the fields on a given line source as a summation of cylindrical waves, which are given here by those Hankel functions. Hankel function is a combination of a Bessel and a Neumann function. Okay, it's equivalent in 2D of the A minus jkr thing. Okay, so this is a cylindrical wave. Okay, so we can write the fields from a given line source as a cylindrical wave, as a series of cylindrical waves. And then, of course, we have to add up the results from the different line sources. And when we do that, we actually do it mode by mode. So these indices, we take the n equal 1 index for this line source, then for the next line source, etc. And then we use the Levine series acceleration formula. Okay. I don't spend too much time on that. It's just to tell you, let me go directly to the conclusion, is that then instead of needing 1 million terms to have a 10⁻³ accuracy, you need 25, which of course is a lot more convenient. So you save orders of magnitude in computation time. Okay. And actually, we first did that on Vivaldi antennas already quite a while ago. Okay, and so essentially it's a tapered slot antenna, so it's fed here. So here there is a hole, otherwise you just short circuit the feed, and this is a tapered line. And we look at versus frequency, okay, at the real and imaginary parts of the antenna impedance. Okay? And we see that if the element is on the edge or near the center of the array, so here we are talking about an array of 32 elements, and depending on whether we are talking about element 1 here or element 16, okay, we have quite big deviations of quite a few tens of ohms in terms of impedance. So that needs to be taken into account if we want to properly match those antenna arrays. And by the way, here, the array has been considered infinite in one direction and finite in the other direction. I will show you why a bit later. Any question at this point? Gunesh, is this the proper rate of explanation?
I think that is excellent. And
okay, thank you.
I'm trying to learn things as I go, Christoph. But can I ask a very quick question before we proceed further? This the coupling between the antenna elements. It is like, I understand it reduces the performance with respect to the direction of arrival algorithms or
for instance, yes.
But also in consideration with the spatial multiplexing to increase the data rate, we need independent channels between the antenna elements. This also means that we need to consider it to understand the actual data rate that can be reached, because it is like a limitation in terms of the data transmission rates as well, I guess. Yes,
definitely. So you may have to undo the effects of mutual coupling. So this supposes, again, you know, what is named the embedded element pattern. So is the pattern of one element in the presence of all the other ones. And so this impacts, for instance, the correlation in MIMO communications. We focus pretty much on the correlations between signals coming from a given source at the level of two different antennas. And that correlation is going to be strongly impacted by the different element patterns we have at the different elements. Okay. But also so that's more from a signal processing perspective. There is also a circuit perspective to this problem, is that actually you need to match the array. Actually my favorite example in that perspective is actually super directivity. You may have heard about that. You have an array and then you say, oh, we are going to scan in a direction that is very close to the axis of the array. This provides you a pretty good directivity. So you introduce a phase shift that is k times the distance between consecutive elements. So this allows you to scan along the array and with a pretty good directivity. And this idea kind of comes back every 5 to 10 years. And even some companies are establishing businesses on this idea. There was 10 years ago, there was a British company that had raised 1 or 2 million pounds to do super directivity on board of satellites. Okay, great, but maybe they missed the fact that labs had looked at this problem long time before. And the trick of super directivity is that, okay, you introduce a phase shift that is k, so the wave number, so 2 pi over lambda times this distance, okay, between consecutive antennas. This allows you to scan on the axis, okay, great, and with high directivity. You can do even better. You can increase even a bit more the phase between consecutive elements. It's as if you were scanning outside visible space. So you scan beyond the horizon. It's perfectly feasible. You just have to increase the phase shift a little bit here, and indeed it produces even higher directivity. And so this gets reinvented every 5 or 10 years. You see the idea coming back, not especially from the antenna community, who starts to know where is the problem. And so what is the problem is that actually, if you make the array relatively large, well, actually the impedance of the antennas is going to get close to purely imaginary. So it gets extremely difficult to match the antennas. Why? Because, of course, the currents on a given element influence pretty much those on the other element, okay? Especially given that they really look at each other, so to say, they scan along the array. And then it's possible to prove that in the infinite array limit, it is just impossible to match the elements, because in the infinite array limit, the impedance must be purely imaginary. So in practice, you can do that. So it is a recommended thing to do. You can use superdirectivity, but typically with just two or three elements, and your gain is going to be 10, 12 dB, okay? But you cannot increase, let's say, exploit this idea much further. Otherwise, you realize that you cannot match the array. So there's a signal processing impact because let's say the intensity and the phase of the signals get distorted by the radiation patterns. But there is also a hardware implication, given the fact that this may cause issues in the way you match the antennas to the transmitters or the receivers. Does that answer your question?
Yes, thanks a lot, Christoph. And I think Raha has a question as well.
Yeah.
I see her hand up. Would you like to ask your question, Raha?
Yeah, thank you, Mr. Gray, for this presentation. I want to ask about the kind of source in a phased array, and if all the sources exist in the phased array have the same values?
Yes, I would say yes and no. If you had, let's say, bachelor's course on antenna arrays, okay, it tells you that if you introduce a certain phase shift, okay, and you have given amplitudes, you can scan the beam. Okay, and actually, the way we look at the problem is that we excite one element at a time. So if I excite element number 1, I get this pattern. I excite number 2, I get this pattern. And when I say I excite element number 1, well, I excite just that element, but the other ones are there. Even the generators of the other ones are attached there. And then you can suppose you say, oh, no, I would like to excite this array with a coefficient 1 here, 2 plus j there, and 5 minus 3j there. Well, you take this pattern times 1, 2 minus j this one, and 5 plus 3 times that one. So we play with the embedded patterns. So that is our, let's say, basic quantity we work with. And then it's just a matter of superposition, because there is one very convenient thing that works with antenna arrays is that as long as you are just adding sources, so you don't add materials, but you just add sources at consecutive elements, well, then the fields just add up to each other. No, it is electromagnetic superposition. Of course, if you're adding another antenna or you're adding an object in the vicinity of the antennas, then fields are not going to just add up. Okay, so the way we analyze arrays is that we look at the radiation pattern of one element when the others are not excited. And then when several elements are excited with different coefficients, well, you take those patterns and you add them up with the same coefficients. And then sooner or later, this forms the beam you're looking for. But given the fact that the patterns are different, okay, you are not going to obtain the same thing as what you had while you were considering identical patterns. Okay, so, and that will be clearly visible in the side lobes. So it's difficult to say, I'm going to control the side lobes while not taking into account the effects of mutual coupling. That's a waste of time, because the level of side lobes will have everything to do with the diversity between the different embedded element patterns. Okay, so you could also say, I'm going to excite all the elements because I know which weight I want to put on every element, and you run the calculation like that. Okay, but since in 5 minutes you may be tempted to have another excitation law, you may rather say, I am going to compute what I obtain when I excite the elements one at a time, and then when I know which excitation law I want to apply, then I will take those different patterns and add them up with the proper coefficients. So this allows you to do a preparatory work that gives all the embedded patterns, and then you don't have to run new electromagnetic simulations when you need, let's say, the array pattern for another set of excitations. Does that answer your question?
Okay, thank you. But I have another question. Just I want to know if you can, if we use the coaxial cable as an excitation source, we can apply these techniques.
Yeah, there are two ways. Either you say that the cable is part of the antenna, or you say that the cable is part of the generator. Okay.
The cable is a part of a generator.
Yeah, okay. Well, then you take a Thevenin equivalent representation of the generator plus cable. Okay. So you can always do that. You know that a generator can always be represented by a Thevenin or Norton equivalent. Well, Thevenin is probably more popular. Okay. So it's an open circuit voltage and a series impedance. And when you add your cable, you are going to change those two values in a predictable way. It's a little bit of transmission line theory to go from, let's say, the equivalent Thevenin representation of a generator to the equivalent Thevenin representation of that generator plus the cable. Okay. But you could also do it the other way around, and sometimes that's something we do. If sometimes the feeding structures are a little bit complex, and so we include them. We say that they are part of the antenna. Okay, but it's a very good question because you have to do something about it. You cannot just ignore the cable. Even if the cables all have the same length, you have to include them in your analysis. And either you include them in the at the level of the antenna or at the level of the generator.
Okay, sorry if I'm asking many questions, well, because I have worked in my PhD on a quick-shear cable. Another question only I want to ask, if the cable is a part of the antenna, what is the difference between if a cable is a part of antenna and a cable is a part of a generator?
There can be a difference. Actually, it's better because I did not want to enter into details, but since you ask, I will. Okay, it is better to include it as part of the antenna because it's not exactly the same. The problem is that there can be some currents flowing on the external conductor of the cable as well. It's not all about the fields that are in the cable. It can be about the fields around and the currents on the cable. Okay, so your cables are going to scatter. Okay, and so because they scatter, they can distort the radiation pattern. And that's why it is actually better to include them in the model of the antenna, because the method of moments, for instance, is going to include those effects of scattering.
Okay.
Of course, the other approach is to have a neat ground plane and to make sure that all the cables are behind the ground plane. Okay. And well, in practice, in the end, it's a trade-off between those two approaches about trying to have a well-defined ground plane, but sometimes there is a little bit of cable that has to be above the ground plane, and then you have to include it into the model of the antenna. Okay. Good. A bit like I showed here in this slide. Well, here, this is the equivalent of the coax cable, and we have included it in the antenna model. Okay, and it's not the same as including it in the generator, because there you are not going to include the effect of the scattering by the external part of the cable.
Yeah.
Okay.
Sure. Okay.
You're welcome. Very good question.
Thank you.
Okay. So now, if I proceed here with the method of moments, don't worry, I'm not going to go through those formulas here. But what if you are dealing with a dielectric object? So this is metal, but this is a dielectric sphere, for instance. Well, then we add extra unknowns, equivalent electric and equivalent magnetic currents at the interface. The equivalent electric currents corresponds to N being the normal, cross the magnetic field, and the magnetic currents are going to be minus N across the electric field. And then, well, instead of just imposing zero tangential fields on the surfaces, well, here we will have to impose the continuity of the tangential component of the electric field and the continuity of the tangential component of the magnetic field. It's a bit more work, but the principles are pretty much the same. Okay? And that's how sooner or later you can compute the scattering, for instance, by an infinite array of spheres. Okay. Of course, I skipped many steps of singularity extraction and Green's function tabulation, etc., etc. But let's say with the basic principles I announced, you can compute the transmission and reflection from or through an infinite array of spheres or any frequency selective surface, 2D or 3D. And this is versus wavelength here, okay, the transmission coefficient, the reflection coefficient, and here is just a check that the total power reflected and transmitted is equal to the incident power, and it got verified within a small fraction of a dB. Why doesn't it work here? Well, actually, when the wavelength is getting too small, okay, means the frequency too high, then the meshing of the spheres is not fine enough compared to the wavelength anymore. And then, so typically the meshings, so the triangles should be smaller than lambda over 10. Okay. Okay, so we can check, let's say, energy conservation, and that's a good way to check the quality of the method of movement code. It's not the ultimate check, but it gives quite some confidence, especially when we see that energy conservation is satisfied within a very small fraction of a dB. Okay, and then you can analyze all kinds of periodic structures, also periodic structures with a defect. So at some point, the periodicity is broken, and then you have a passband in the middle of a band gap. Okay, and that's and here you have little symbols that are superimposed on results obtained with finite elements, and we see that we have a very good match. But now the difference is that we have to mesh only the surfaces. Okay, here more validation examples with little patches in a dielectric layer. Okay, now when structures are getting big and complex, and for instance the feeding structures are getting complex, well then you may need a lot of basis functions, typically a couple of thousands per antenna. And if you're analyzing pretty large antenna arrays, which themselves have hundreds or even thousands of elements, you get into the millions of unknowns, and that's where it can get very slow. And actually, what we did is to include, of course, the aspect of the periodicity of the structure. So at the element level, we didn't do much effort to reduce the number of triangles or to find analytical approximations. But the time saving we exploit, we try to leverage, is at the array level. Just because we are talking about identical elements, of course, there's a lot of computation time to save. However, it's not because the elements are identical that the currents are going to be identical on the elements. The elements near the corners or the edges are going to have completely different currents from those in the centers, especially for these wideband antenna arrays. So actually 20 years ago, I've been working with the Institute of Radio Astronomy in the Netherlands, and actually they were working on these arrays of Vivaldi elements, so these tapered slots, but they're really connected physically with each other. So they're really soldered with each other. So that means when you excite this element, the current really flows on all the elements. Okay, so it's really a coupling machine, and you really cannot neglect mutual coupling. So that's where mutual coupling is not an edge effect, it's not a side effect. It is how the thing works. And why are those arrays so strongly coupled? Because this strong coupling allows you to make very smooth surfaces. And smooth surfaces is what you need. Well, at least it's a necessary condition if you want to have wideband operation. So for us, it was a very nice opportunity to see if our methods that predict the effects of mutual coupling truly work, because this is probably the worst example you can imagine in terms of strongly coupled array. So there are many approximations that may work for dipoles, but that won't work at all in this type of arrays. And one possibility, again, I'm not going to go through the details. One possibility is to analyze arrays that are finite in one direction and infinite in the other direction. Why infinite? Because, well, then you can work with a single cell. You use these periodic Green's functions which have been drastically accelerated from 1 million terms to 25 terms. Okay, and then you analyze one element. It's as if you had analyzed all the elements on the infinite array. Okay, so infinite in one direction and then finite in the other direction, and even finite in that direction. Since the elements are the same, there are some tricks to more rapidly solve the problem. From a mathematical perspective, we are talking about tuplets. We are generating tuplets matrices, so matrices with interesting structure that can be solved faster. Okay, and then we make, if we have an array that is finite, which of course by essence is finite in both directions, we can combine results with the array truncated once along x and once along y, okay, to try to approach as well as possible the radiation patterns, the actual radiation patterns. So you take a picture of this array, so to say, okay, and then you see it from the top. And so here, that's what you have here, okay? In Belgium, we named that a koopfrit. It's the instrument you use to cut fries, right? So it's just this array seen from the top, okay? So this element is the corner element. This is an element in the middle of the edge, the middle of another edge, and the element at the center or near the center. Well, if the array were infinite, well, all the radiation patterns would be the same, okay? Here for the vertical polarization and here for the horizontal polarization, okay? But that's not reality. Just because those elements have quite different environments, the radiation patterns are going to be extremely different. And the difference can be up to 5 dB. Again, that's why it's not just a side effect, especially in the strongly coupled ultra-wideband arrays. And in particular, it produces, so this is a sphere seen from the top, and you really color the sphere with the value of the radiation pattern depending on direction. So you see here for radiation near the horizon, you can have very high values for the radiation pattern, which you don't see at all in the infinite array solution. Where does that come from? It comes essentially from radiation from currents that are floating up and down on the edges here, which you don't have in the middle of the array. Okay, and well, typically by this combination of arrays that are finite first along y and then finite along x, we manage to represent quite accurately. So these are the errors we produce. So this is the exact solution, okay, for the radiation patterns of those different antennas, and these are the differences, the errors we produce, and we have big errors near the horizon, okay, but even long before you reach the horizon, the errors are pretty big already. They can be typically 50% error, okay, and so these are not acceptable errors, but if you combine those results with arrays being infinite in one direction and then in the other direction, you get a much lower error. There is still an issue in the corner for the reason I explained a minute ago about the current flowing in the corner, and we came up with a fix for that, but that's a bit nitty-gritty, so to say. So I'm not going to go through this. Now, later on, we wanted to also analyze non-regular arrays, and then, of course, those techniques don't apply anymore. Because it's based on arrays being infinite along x or infinite along y, and then we had to come up with completely different techniques. Any question at this point?
I don't see anything in the chat box, Christoph.
Okay, good. So please stop me if the issue is that you feel I'm speaking a completely foreign language, okay, despite my Belgian accent. So actually, what happens in a finite or infinite array? Well, you know that we are pretty much focused on the embedded element pattern. So we like to know what is going to be the radiation pattern if we excite just one element and the other ones are passively terminated, okay? Good. And then if we excite, we can do that for the next element, and if we happen to excite all the elements, we add up the results. That's not a big deal. So the basic quantity is the embedded element pattern. So what is radiated when you excite just one element? Or more precisely, what are the currents flowing over the whole structure when we excite all the elements? By the way, if you have the currents here, for instance, while you excite there, you also have an element of the admittance matrix. So this also allows you to get the admittance matrix of the array, which of course may be also very useful if you want to match the array. Typically, you excite one element. Well, there is going to be current on all the elements, which has been represented here by this red curve. Of course, this curve is not representative of the actual current flowing on the elements. On this antenna, the current looks rather like this. It's pretty much concentrated along the slot. So when I drive this curve, it's just to say that the current on consecutive elements is going to decay, but on each of the elements, you have a quite complex current distribution. Yeah. But you can talk about kind of a wave of current that is propagating over consecutive elements. And when you have an eigenmode, even that wave may happen not to decay at all. Okay, so then the wave is kind of guided by the periodic structure. Okay, but okay, in most cases it will decay, but nevertheless, by the time it reaches the edges of the array, it can be still significant, such that it gets reflected by the edges. Okay, and that's what most approximations omit. And maybe it's kind of okay for arrays of dipoles, but for arrays of Vivaldi antennas, you really cannot neglect that effect. Now, there are quite a few techniques that have been developed over the years for analyzing finite periodic structures. So that's been a cup of tea, let's say, in the years 2000, to say. You may say, well, when I'm going to excite all the elements, I'm going to produce the current distributions very schematically represented by the red curve. You're going to reproduce them at each position where you excite. So you're going to have one here, you're going to have one there due to this element and so on. And so you're going to add up with something that looks like this. Okay. And what you should not do is brutally truncate here the solution. So here we're talking about the currents on the elements. You cannot just truncate here because you are going to include current here on the left edge that is due to an element that doesn't exist here. Okay, so that is something you should not do. Okay, so what would be interesting is to have a trick to analyze those currents that are floating over consecutive elements when you excite just one. Okay, and then you just copy them on consecutive elements to have something that is already much closer to reality. You only turn on the existing elements. You don't turn on non-existing elements. Nevertheless, you are still going to miss the reflections by the edges of the array. But I'm going to deal with that later. Okay? So a new challenge, so to say, is to consider an array which so far is infinite, where you excite just one element and you want to find the currents over all the other elements in the infinite array. As you see, it may be very useful to give already a very good approximation of what's going to happen when you excite all the elements over the finite array. You are going to miss only these reflections, okay, which are, let's say, important but not dominant, so to say. Okay, let me skip this slide because I have 80 slides and I covered only 20 so far. So I have to skip some of the material. But I'd like to show this. This is the magic formula that allows you to get the current on element M when you are exciting element 0. Okay, and you do that. So you excite only element 0, and you want to look at the current on element M. Well, suppose you have a software. It can be any software. It can be your own method of movement software, or it can be CST, HFSS, or whatever. It's a software that gives you the currents when you excite all the elements, so infinite array solution, with a certain phase shift between consecutive elements. So that's important. You can include, you play with the Green's function such that you include a certain phase shift between currents on consecutive elements. It's not a big deal when playing with the Green's functions. I don't have the time to enter into the details, but let's say practically all commercial softwares can compute that for you. But here, all the elements are excited. But you put this in this kind of Fourier transform, okay? So you integrate the phase shift, you take every possible phase shift between 0 and 2 pi, and you add this Fourier kernel, and then with the m here in the exponent, and then you get the current on element m when you excite just element 0. Okay, and that's very convenient. The only thing is that when you calculate this integral, well, you have a finite time, unfortunately, to do the job. So you have to replace the integral by a sum. And maybe you remember that so this is kind of a Fourier transform, okay? And if you sample a function in one domain, you are going to repeat it in the reciprocal domain. So typically, when you replace the integral by a sum, you are implicitly exciting the element, the array, periodically. Okay, how often? Okay, well, this distance between excited elements just corresponds to the number of terms you put in this Fourier integral. Is it a problem? Well, yes, as such, you are not going to have a good approximation of what happens when you excite just one element. You're going to have this, and it looks pretty horrible. You can avoid it by having more terms, but it's going to take you more time. Okay? So that's where we combine spectral approaches with spatial approaches. When I say spectral, I'm referring to this phase shift. And this is in the reciprocal domain. It's in the Fourier transform domain. So this is a spectral thing, to say. And spatial, well, that's where I'm going to talk about macro basis functions. So the thing is that this sounds like a good trick, but the computation time may be too big if you want to reach a sufficient number of points of terms here, such that the aliased sources, it's really a aliasing problem associated to a Fourier transform of something that has been sampled. Okay, so the aliasing problem may be too big, you may need too many terms. But in the end, what we do is something different. Let me skip this because I'm going to miss a lot of time. Okay, what we do is something different. And this is something that has been pushed pretty much by Professor Bitra, though in the years 2000. But in the 90s, some people conceptually got pretty close to at EPFL or in Ghent, University of Ghent. Okay, it's another idea. The problem is that we have to mesh very finely the surface, and you know, this is still. Well, the mesh I showed you is still very coarse. This one has 100 basis functions, but typically you would need 1,000 basis functions. Okay, so you may try to reduce the number of unknowns per antenna. Okay, and typically you may try to go from about 1,000 to about 10. Okay, and how to do that? Well, we typically define a limited number of such distributions. And we say that the final current distribution on a given element is just a linear combination of these 5 or 10 current distributions. And typically, if the antenna is smaller than the wavelength, which is most often the case, okay, you won't need more than 5. Something like that. Okay, so it really scales with the size of the antenna in terms of wavelengths, how many you need of them. Okay, so you say that your current distribution is a linear combination of a few a priori computed current distributions. Okay, so it's just like a traditional method of moments, except that your basis function is not just defined over 2 little triangles. It's a whole current distribution which you have pre-computed. Now, you may say, yes, but how do I determine those pre-computed current distributions. There are quite a few techniques. Okay, let me skip some math here. There are quite a few techniques with the current on the antenna, with a number of current sources around the antenna, or excited by different plane waves, or excited by different neighbors. And so there is no ultimate technique, so to say. However, what we observed is that those different techniques are, in terms of performance, are pretty close to each other. Okay? And most of the time, the issue is not about determining those typical current distributions. It's interestingly, okay, you may use these different techniques. If the antenna is about half a wavelength, you will need 5 or 10 of them, okay, and independently of how they have been determined. Of course, more systematic techniques to determine them would be interesting. Now there is this theory of characteristic functions that has been revived, that Harrington developed in the 70s, that is being revived now. It's yet another technique to find those equivalent currents, but in our experience, it's not a big challenge. You take 10 current distributions with very different excitations, and it's going to work with very high accuracy. The challenge is rather about the computation time, because now when you will have to compute the interaction between those macro basis functions, you will need first to refer to the interactions between the small triangles. And then you will think, oh, I saved no time, because typically to get those interactions, I have to anyway pre-compute the interactions between the millions of little basis functions. Well, essentially, a lot of our work has consisted of skipping that step, of having a direct interaction between those macro basis functions without ever talking anymore about the little basis functions they are composed of. Okay, so is this goal clear to everyone? Okay, and so this is, for instance, a picture from Rob Maskan's thesis. So he's now a professor in Sweden. He did his PhD in the Netherlands, and he shows those typical current distributions for Vivaldi antennas. Okay, and you see here, well, it's pretty different for the edge antenna and the center antenna. You see on the edge antenna, you have this dipole current, which produces radiation at the horizon, which this one is not going to produce. Okay. What we came up with is a relatively systematic way of getting those, let's say, characteristic basis functions or macro basis functions. And actually, again, I have to skip a bit of the details, but actually the conclusion is that we are going to take those results obtained with the array scanning method. Okay, so we try to obtain this. In practice, we obtain that. Okay, please keep in mind that this is composed of a current distribution here, another one here, another one here, and there is an interference with the helioscopy. But no, we are not trying to get immediately the fields due to one element excited. We are just trying to obtain good macro basis functions, which is a lot weaker goal. It's a lower challenge. Okay, so you may have interference here, but still include the result in your macro basis functions. Why? Because, well, this interference looks very well, it's just the same as the current you have here. Okay, and at this point, we are not looking for the solution, we are looking for good basis functions. And so this does a very, very good job. Okay, we typically reduce the number of unknowns by a factor of 50. Okay, and still the accuracy is very good. And let me show you an example. So we have an array of 5 by 5 elements. We excite just one. Okay, and we want to see the radiation pattern. Okay, well, the radiation pattern is strongly impacted by mutual coupling, but with this method, the error is 50 dB below the exact solution. Well, let me show this example. I'm sorry for the curves not to be very clear, but I hope you can distinguish the red, green, and blue curve. Okay, so this is the index from 1 to 25 of elements along the array. Here we excite all the elements, is the exact solution. Interestingly, you see that you have a deviation of 3 to 4 dB. So the elements are the same, the excitations are the same, but the currents are not the same because of the effects of mutual coupling. The elements on the edges don't see the same thing as the elements near the center. Okay, and that's why there's this big deviation. But with these macro basis functions, themselves exploiting the array scanning method, you can catch very well the currents, and the error is more than 50 dB below the exact solution. And here we used only 4 macro basis functions. If you happen to use 16, your error is going to be even lower. And that's where, let's say, spatial considerations and spectral considerations meet each other. Okay, so it's difficult to say, oh, I have to do everything in space domain or I have to do everything in spectral domain. Usually it's going to be a combination of both that is going to provide an optimum. So the macro basis functions, which correspond to currents on a given element or a certain typical current on a given element, well, they are our spatial filter. Okay, while the infinite array solutions, they are our spectral solution. Okay, they correspond to a specific phase shift between elements, and all the elements are excited, so it's not localized at all. And those ones are going to be very good at detecting surface waves that are guided by the periodic structure. So this array scanning method combined with the macro basis functions, well, in a sense, they are a way of combining spatial and spectral domain approaches. Now, I'm afraid I'm pretty much behind schedule, so I would like to ask Gunesh how much time I have left.
Christophe, I need to go to my class at 12:30, which means 24 minutes.
24 minutes.
Okay. If we can, including the questions, we can wrap it up in 24 minutes, it would be awesome.
Including the questions. But I propose we proceed with asking questions during the presentation.
Okay, excellent.
So if you have more questions about this array scanning method, okay, or macro basis functions, it's the proper time. So I hope I didn't kill you with too many equations. Huh? There are relatively few, I think I can say that, but I hope these concepts of, let's say, infinite array solutions, okay, and let's say, and how we go from infinite array solutions to solutions with one element excited only, okay, I hope I managed to make that relatively clear, okay, and it's all in that array scanning method that's been proposed actually in a paper that had a very different goal, okay, by Ben Munk in 1979, but it's been kind of unnoticed for a couple of decades before it got used in array problems. Okay, so let me skip a lot of stuff. By the way, we can also analyze for a certain phase shift between consecutive elements, the current distribution, rather than going to be focused around the edges of the metallizations, they are going to be all over the metal plate, because it's kind of a wave that is guided by the waveguide made by the parallel plates. But the infinite array approach allows you to catch them very well. You just have to look for which phase shift between consecutive elements, the determinant of the system of equations is getting close to 0. That's where you have a solution without having an excitation. In linear algebra, when you say Ax equal b, okay, you can have a non-zero solution for x while b is equal to 0. Okay, so that means you would have fields on an array while you don't excite any element. It is perfectly possible. Okay, you just have to see whether or not the determinant of the system of equations is 0. If it's 0, you can have non-zero fields with 0 excitation. It's an eigenmode that circulates over the array, and of course, designers of phase arrays hate that. while designers of meta surface antennas, they love that. Okay, why? Because meta surfaces are actually focusing on fields that are radiated from a surface wave. Okay, so I'm going to skip maybe half of the presentation here. This is just about faster calculations. Okay, so there are more equations, but I just skip them because I'd like to tell you a few things about meta surfaces. So you probably heard that meta surfaces correspond to hundreds or thousands. We rapidly get to 10,000 little patches over a given surface on a substrate. So it's pretty easy to fabricate. Okay, and you just have a feed here. You have a surface wave over the structure, but the periodicity of the patches is kind of broken. So the patches, they change their orientation and sizes slowly but surely. So you cannot exactly talk about a periodic structure. So there's kind of a modulation in the periodicity of the structure. And because of that modulation, well, the surface wave is disturbed and you create leaky waves. And then if you design your antenna well enough, well, you can give to those leaky waves a certain radiation pattern. Okay, so that's been our goal, mainly with Modeste Baudéou. Okay, we tried to give a specific shape to the radiation patterns of meta-surface antennas. Okay, and we did that based on the method of moments. Okay, we are looking for eigenmodes, so for solutions that can circulate. So the surface waves, they correspond to solutions of the method of moments while there is no excitation. So we just look for the determinants of the method of moment matrix. We want those determinants to get close to zero. And then, okay, once you've been catching those surface waves, you can replace this the patches here by a continuous surface impedance sheet. Okay, so that surface impedance sheet kind of comes in parallel to the transmission line that is represented by the thickness of the slab here. Okay, you probably heard that you can analyze multi-layer structures as plane waves that are propagating along equivalent transmission lines. Well, then you create a sheet impedance that here comes in parallel. Okay, and it's all about designing that sheet impedance, knowing that usually it has 4 parameters because it can be anisotropic. Okay, so there's a ZXX, ZXY, and so on terms here. So you have 4 terms, and that can vary along the surface. And we try to give a variation such that the radiation pattern is going to be controlled. And so here again, it's our method of moment, well, our integral equation. We have the incident field plus the field that is re-radiated by the currents must be not equal to 0, but it must relate properly with the currents given the surface impedance that is represented by the sheet here. Okay, so except for this term, we had seen those before. This is the convolution between the Green's function and the current. By the way, the Green's function includes the effect of the slab. Okay, but here it's not equal to 0. It is equal to a field that is in proper proportion with the current. And how is that proportion given? Well, it's given through the surface impedance that is located, that is related to the local periodicity of the patches. Okay, and actually here we are going to transform the method of moments from an analysis tool into a design tool. It would be great if we could say, oh, we take a given radiation pattern, we want a given radiation pattern, okay, and please give us the dimensions of the 10,000 patches. Okay, well, if you, let's say, transform a bit the method of moments can do that for you. Okay, so you don't need any optimization. Okay, So you come up with a different version of the method of moments that is going really to tell you what that surface impedance needs to be to have the current you're looking for. Okay, so initially in the analysis problem, you know the surface impedance. Okay, you have a certain excitation and you look for the current. But now you say, oh, I know the radiation pattern, so I know the currents I should have on the surface. Okay, and then you say, oh, I know the current I have on the surface, so now the unknown is the surface impedance. Well, we find the surface impedance. Okay, so it's a new version of the method of moments that gives you the impedance and in the end the shape of the patches, okay, to radiate a certain radiation pattern. Okay, and what's the trick? Well, you can decompose the current into a number of basis functions. We use full domain basis functions. Okay, they correspond to Fourier-Bessel functions. So versus phi, they are a phi, a to the j phi functions, and versus rho, versus radial direction, they correspond to Bessel functions. So you see Bessel function, okay, with a 0 at the end of the structure. Okay, okay, good. But you can also do the same thing for the impedance. Okay, you say, I don't know the impedance. Okay, well, you decompose it into a number of known basis functions, for instance, these ones. Okay, but you don't know the coefficients. Okay, doesn't matter. You don't know the coefficients, but it's a traditional method of moment problem. You put that in the system of equations, okay, and you solve in the traditional method of moments way. I have to say there is an issue there. Is that, well, you know the radiation pattern, so you know the desired current on the antennas. Well, yes and no. The problem is that you only know the visible part of the currents that are able to radiate. Okay, if the currents on the surface oscillate too fast, we are talking about a slow wave, then it's not going to radiate. Okay, so there is an issue, is that we don't know entirely those currents. We know only the radiating part that is going to produce the desired radiation pattern. Okay, so what about the invisible part? Okay, well, the invisible part corresponds to the surface wave, and we made a pretty simple approximation. We just said that it corresponds to what we have when the patches are not modulated. So when the patches are all identical, so without disturbing the surface wave. It appeared to be a good approximation, astonishingly good approximation. And I will say a few more words about that later. Okay, so supposing you make that approximation, well, you know the surface wave, you know the current that is needed to radiate your radiation pattern. Okay, so you know J, but you don't know ZS. Well, ZS, you write it as a number, as a superposition of known current distributions. For instance, these full domain functions, Fourier-Bessel basis functions. Okay, you insert that in the method of moments. You use testing functions. You get a square system of equations, and you find all those coefficients. So you know how the surface impedance should look like as a function of coordinates to radiate your radiation, the needed radiation pattern. Okay, so this is actually the Fourier transform of the currents. Okay, and this is the inside here. You should have the visible region, but there isn't much here because here we consider patches that are all identical, and we are considering phase shifts for which there is a surface wave. And you see there is a lot of current outside the visible region, so those guys are not going to radiate, and in the radiative part there isn't much here. Okay, while in the actual antenna you are going to have something in the middle here that is going to radiate. Okay, and well, in the end, these invisible currents, they are not so different from those you had before your metasurface was really a metasurface, so with identical patches everywhere. So that's the assumption we made, but we can iterate. Once we will have a design, okay, that works reasonably well, we are going to again look at the invisible currents in that design, and we are going to reinsert that as our initial guess, or as a new guess for the invisible part of the currents. Okay. I skip the algebraical details because I would like to leave a little bit of time for the questions. Okay. But what we try to do based on this is some cosecant array, cosecant radiation pattern. Okay, so this is ideal. Of course, it's extremely difficult to obtain. To have those sharp edges, you would need an infinite antenna. Okay, but in the end, what we get is this, which is kind of reasonably close, if I may say that myself. Okay, and so the radiation pattern seen from the top, so as drawn on the sphere, is what you have here. Okay, and then we can also design multiple frequency antennas. Okay, with multiple patterns, multiple maxima, and again we use the method of moments to do so. So there is no optimization. So we end up with the 10,000 patches, but without having run any optimization. It's a direct method. Okay. And here our first experimental validation. We knew that conical patterns were very difficult to realize with metasurfaces. So we've been targeting that. So this is a cut of the radiation pattern. So it should be axially symmetrical. So that creates, so it's a conical pattern with the opening at 25 degrees here. Okay, and so that's the antenna realized. So here you can zoom on the patches. You see that all of them are different, though there has been no optimization run there. Okay, and we got the blue curves while the desired is red. Okay, well, we get pretty well the let's say the conical pattern, though we still have relatively high patterns at broadside. Okay, so that needs to be fixed. In part, it's due to the tolerance we had, the limited tolerance we had with the realization of the patches. Okay, but we are also investigating other possible sources of discrepancy, like scattering by the edges of the ground plane.
Christophe,
okay.
May I interfere for a moment? Yeah. Oh, this is, but I don't want to hijack the Q&A discussion. Mansour will lead the discussion later, but I have a question that I couldn't resist asking at this point.
Sure.
This experimental validation is very impressive, clearly.
Thank you.
And I understand that the frequency, the selected frequency is, the approach is rather flexible towards the selected frequency band. Is that a correct understanding?
Yes. What we realize, and that's a good news about such metasurfaces, is that they are not so narrow band. You certainly witness that the main criticism against metamaterials is very narrow bandwidth. Well, those metasurfaces, they easily get a bandwidth of 2, 3, 4%. Okay, so that's one good news. And I can also show you comparisons at other frequencies. We had actually, there's going to be a paper on a special issue on metasurfaces that's going to appear in the magazine of the IEEE AP Society. And so there's going to be more details about this experimental validation in that paper. I would say over a couple of percent, we have a good match between so a couple of percent bandwidth, good match between desired and obtained radiation patterns. Having said that, the group of Stefano Macci showed a metasurface with a 30% bandwidth. Okay, there's only a little trick there. Okay, well, little trick, not easy to realize, by the way, is that there is a price to pay in terms of aperture efficiency. So the antenna kind of gets bigger because you have different portions of the antenna that take care of the different frequencies. But at least we can say that the ultra narrow band challenge of metasurface has been solved, essentially. So I think nowadays we can talk about bandwidths of 2, 3, 4%, And I'm pretty confident that in 5 years, we may get close to 10%.
That sounds like excellent news.
Thank you. Of course, it is still a bit of wishful thinking, but we see that our results and also those of some other labs are going pretty well in that direction.
Very good.
Okay. So essentially, I hope now, what is the time now?
Yeah, we are on time. Mansour will continue. I'll need to
okay,
leave
good.
earlier, but
okay, good.
And there are a couple of questions popping up. We can address later, so I don't want to interfere further. Thanks.
Okay, good. Good afternoon.
Thank you.
Thank you. So to conclude, what used to be a nightmare for phased arrays became a dream for metasurfaces, and we are talking about surface waves. So it's still a challenge for ultra-wideband array design. For a certain angle, a certain frequency, you're going to have surface waves, and that's going to completely destroy matching in those conditions. So that's how some radars, ultra-wideband radars, can have blind spots. Okay, and it's still an unsolved problem, but at least this problem is exactly what is being, let's say, exploited to design metasurfaces, because there is a gradual change in the periodicity that turns the surface wave into a leaky wave, and then we can use the method of moments to let's say control those leaky waves and try to match to a specific radiation pattern. What about the next challenges? Well, certainly scanning metasurfaces. We published a paper a couple of years ago. We started to do that just a little bit. Okay, we have just 2 feeds. Okay, and we can scan let's say a 20 or 25 dB gain pattern over just 1 beam width. It's not much, but we hope it's the beginning of something. Okay, and probably let's say a specific combination between phased arrays and metasurfaces should be looked for. And suppose we do that, we should not be afraid of mutual coupling. Actually, suppose we have just a few feeds over a metasurface and that becomes a scanning structure, for sure we should expect that when you excite any one of those feeds, you excite actually the whole surface. But that's not a problem. So it's a full coupling, okay, but that doesn't prevent you from creating proper embedded element patterns, and in turn for creating good scanning structures. Okay, so this concludes my talk. I hope, despite skipping many of the slides, I could manage a good thread through this presentation, and I understood we anyway still have quite some time now for questions and answers.
Can I start with this question? Thank you, Christophe, for this excellent presentation. My name is Shahin Ergizian from École Polytechnique. My question is, you have tried to show us some frequencies, and at the end it was millimeter wave. Can we think about scaling all these approaches at terahertz frequencies?
Yeah, it is definitely scalable. And now we are moving to, so the validation I showed you was around 24 gigahertz. We are currently moving close to 77. And we believe that up to 200, those techniques are going to work. Of course, there is a bit of stress on the tolerance in terms of fabrication. Okay? But we are not talking, let's say, standard lithographic quality should be sufficient up to 200 gigahertz. But okay, now when I say standard lithographic techniques, it's really lithography as it is used in microelectronics. So probably a challenge will be to be able to do that over sufficiently large surfaces. but at least the fabrication techniques are existing.
Okay.
We may not say the same about optical frequencies, because if suppose we want to take this type of leaky wave metasurfaces to optical frequencies, we'll need to be able to control the volumes and surfaces down to let's say 10 nanometer, and there, let's say, the technology is probably not ready yet. Okay? That's why you also find lots of metasurfaces at optical frequencies, but then we are not talking about metasurfaces with just a pin feed and a surface wave on a slab. They are more in the sense of transmission type metasurfaces with the substrate, which is easier to fabricate. You don't need to control, let's say, the surfaces to such a small fraction of the wavelength. You see here near the feed point, it is still useful to be able to control, let's say, things down to lambda over 50, no? Which is quite challenging. But again, if you go to 200 gigahertz with lithographic techniques, it must be possible. At optical frequencies, the technology is not ready yet. Okay. Okay. So that's why I believe that it's scalable to millimeter waves and getting closer to terahertz. But we will need a lot of help from completely other different fields of research to get those things to work at optical frequencies. But for optical frequencies, there's a whole other branch of metasurfaces that are being developed now, that are either in transmission or reflection form, where the patches are not close to the feed points and where the tolerances are rather lambda over 10 rather than lambda over 50.
Okay. Okay, thanks a lot.
You're welcome.
Thank you, Professor Christophe, for this insightful and quite a lot of information to digest. Thank you so much.
You're welcome.
So, is there anyone, so there is one question in chat box, I'm gonna read it to you. Aaron asks, would like to know the mission capacities used for the optimization of metasurfaces computations.
So the computational capacities to do the optimization.
Yes.
Is that, yeah. Well, actually, in the designs I showed you, there has been no optimization. And so those designs, well, the one, yeah, this one or that one, the design time, okay, has been less than half an hour on a laptop. So you have about 12 or 15,000 patches to arrange, so to say. So you could say, oh, we have about 40,000 parameters to optimize, but actually it's not the way we do. We have a direct method that gives us the surface impedance as a function of coordinates. And then there are very good papers that have been based on eigenmode analysis and that tell you how a given patch should look like to have a certain surface impedance. Okay, so in that sense, the computation load is very small, so you can compute them much faster than you fabricate them.
Thank you so much for your explanations. Is there another question? Any other question? So we officially reached the end of this event. It was pretty nice and very insightful. Thanks for audiences for participations. Of course, I'm gonna thank Professor Christophe on behalf of Professor Güneş. She had to leave to class and there was no way to escape from it. So that's what she wanted.
It's a good reason for leaving.
Yeah, that's why she wanted us. She wanted me to thank you for being here with us today. And hopefully we are gonna meet you again one day in person after this COVID.
I'm pretty confident about that.
Thank you so much for audiences. So the recording will be available subject to having some confirmations from workshop chair and of course the speaker to audiences, and it will be uploaded to YouTube channel and our website. So in the meantime, Stay tuned in our website, and we will have the next session of this event on February 8th. And more information will come. Thank you so much, everyone. Thank you, Professor Christoph, once again.
My pleasure. Thanks a lot for your very kind invitation and your excellent questions.
Thank you, and I wish everybody a very good year ahead, and hopefully we're going to meet you again. Thank you, and
Certainly.
have a good day.
Thank you very much. Bye-bye.
Bye.